physics. I know a lot of people are having trouble with the gravity webassign, so I wanted to go over some of these questions with you guys. So this is the gravity webassign. Let's look at it, okay? So remember when you're looking at this first question, the Earth and the Moon are gravitationally attracted to each other. Does the more massive Earth attract the Moon with a greater force, the same force, or less force? Remember that forces come in pairs. Come in pairs. Okay, and they are equal and opposite directions. Opposite directions. So think about that when you're answering this question. So when the Earth pulls on me with its gravity, I'm also pulling on the Earth with the exact same force. The exact same force. It's just that the acceleration or the change in velocity I experience is different because I'm so much less massive than the Earth. Okay, so think about that. Forces come in pairs and they are equal and opposite in direction, but their magnitudes, which is their amount, should be the same. Okay, it's always the same. That's the hint. That's not just a hint, that's the answer. Okay, let's talk more about the mathy ones. If we assume down is negative and we have a 3.5 kilogram rock near the surface of the Earth, what is the force of gravity on the rock from the Earth? So let's look at this one piece at a time. So we have something with a mass of 3.5 kilograms. Here's our rock, okay? And it is, what is the force of gravity on the rock from the Earth, okay? So here is our rock being pulled towards their much more massive Earth, and this is where you have to think about the formulas we've been working on, okay? So I'm gonna write some knowns up here, okay? So we know the formula is Fg m1 m2 over the distance between those two things squared. So in this case, our rock is m1 because this is mass 1 or object 1. Okay, so in this formula, m1 equals 3.5 kilograms. Okay, m2, so we can check that off our list. M2 is the mass of the Earth. Okay, because the Earth is, hello, what am I doing? No, you can't even see that. The Earth is the second thing we're looking at, okay? So mass 2 is the Earth, and so you're going to need to look up in your work what the mass of the Earth is. So what is the mass of the Earth? Does this give it to us? Nope, let me look that up real quick. Okay, the mass of the Earth is 5.972 times 10 to the 24th kilograms, okay? That's very, very important that you don't forget that 10 to the 24 power, okay? So that's important. We know what G is. We're given G. It's 6 oh, that's my cat. Move it, cat. All right, thank you very much, cat. 6.676, I believe, times 10 to the negative 11th, and that's Newton meters squared per kilogram squared. Let me make sure I'm right about that. Da-da-da-da. Gravitational constant. Yeah, 6.67 is what we're giving. So 6.67 times 10 to the negative 11th. Cool. So we've got G, we've got mass 1, mass 2, and now we just need to know the distance. So, oh, there's another cat. That's fun. Great. Okay, so we need to know the distance between the rock and the very center of the Earth, because whenever two things are moving towards each other, we approximate how far away they are from their center of mass, and the center of the mass of the Earth is just its radius, or sorry, but the distance from the edge of the Earth to the center of mass is the radius of the Earth. So let's look that up real quick. Radius of Earth. Nope, in meters. All right, so if you look this up online and you got something weird about miles because you were doing something different, so you should know that the distance is 6.378, or maybe I think we gave it to you this way. Distance is 6.378.100 meters, okay? Awesome. So now we have D squared. Yay, we have that. We have everything we need to calculate force, but these are some very gross looking numbers. How can we make this a little bit easier? Let's do it piece by piece, okay? So we're going to say we know the formula, again, is F equals G m1 m2 over D squared. So let's blow it up and we'll take it into different parts, okay? So F equals, and then what's G? I'm going to write in different colors for this, okay? So I'm going to say the numbers part, I'm going to do in one color. So G is given as 6.67, sorry, times 10 to the negative 11th. Awesome. And then I'm going to pull out another color for, did not color coordinate this well, for the units. 10 to the negative 11th Newton meters squared per kilogram squared. And I'm going to go ahead and I'm going to extend that line all the way across like this, just because. And it's going to be easy in just a second. So all of this whole thing is G. And why did I write it this way? Because I'm going to show you how to rearrange stuff. So G times what? G times the first mass. And the first mass we said is 3.5 kilograms. So times 3.5. And then my unit is kilogram. Oh, I forgot to put this as kilogram squared. Okay, cool. Now, what's next? Mass 2, which was the mass of the Earth. So 5.927. By the way, these are the numbers I have. They're not as far as the 3.5. Your number might be different, so don't put in my answer. Okay, 3.5, so 5.927 times 10 to the, so my 10 to the was this, times 10 to the 24th, and then kilograms. Kilograms. Awesome. Now remember on the bottom, it's divided by the distance squared. Okay, so down here, I already have something already here, so I know it's going to multiply by whatever comes next. So multiply times the distance, which is, and it's going to be squared, so I'm going to put parentheses, 6, 3, 7, 8, 0, oops, sorry, 1, 0, 0 meters. Oh, then I want to put that in this color. This is very messy. Let me redo that. Okay, let's just redo that. Ignore this part. 6, 3, 7, 8, 1, 0, 0, and then the unit is meters. Meters, and remember this whole thing is squared. All right, cool. So I'm going to take this part by part. I'm going to move stuff around. I'm going to go ahead and do this part in my calculator. If I can find my calculator. Ooh. Awesome. Hopefully you have your calculator. Remember, you should have a scientific calculator by now. If you don't yet, tell your parents you have to have one. You guys, I don't have like graphing calculator. I'm fired. What's happening? Okay, so I'm going to approximate what you should be doing. Okay, so let's do this instead. Okay, so I know that this thing has to be squared on the bottom, so I'm going to go ahead and square that. So let me pull up a calculator. Calc. So in my calculator, I'm going to put 6, 3, 7, 8, 1, 0, 0. And I'm going to square it. It's not going to let me. Okay, 6, 3, 7, 8, 1, 0, 0. All right, cool. So that gives me this actually kind of crazy number on the bottom. And I'm going to write this again here. You'll notice that if you put that in your calculator, you get 4.07 times 10 to the 13th. Except your calculator says E. Remember, we don't believe in E when we're writing it, okay? And remember, also, we have a unit of meters squared now. And don't forget, we also already had kilograms squared from here, okay? So when I put this number in my calculator, I end up with 4.07 times 10 to the 13th meters squared. And then I already had that kilogram squared that was here. That's what the bottom looks like now. Cool. On top, I'm just going to rearrange stuff. So I'm going to put all my numbers together. 6.67 times 3.5 times 5.927. And then I'm going to put all my 10 to those together. Times 10 to the negative 11th times 10 to the 24th. And I didn't have one for the middle. And then I'm going to put all of my units together. Okay, times Newton meters squared for that one. Over here I have a kilogram, and over here I have a kilogram. Awesome. So I'm going to go through and I'm going to do what I think is easiest. I'm going to start canceling stuff out. Okay, I'm going to cancel out that meter squared and that meter squared. Awesome. I'm going to cancel out that kilogram squared and that kilogram squared. Also awesome. Now I'm going to put in my calculator 6.6. Oh, you'll notice, by the way, that leaves, this is going to be your only unit. Boom, that's your unit. That's all that's left. And it makes sense because force is given in newtons. Sweet. All right. Let's keep going. So now I'm going to do 6.67 times 3.5 times 5.973 927. And then I'm going to divide that by 4.07. Okay, let's see. 6.67 times 3.5 times 5.927. I'm going to divide that by 4.07. And I end up with, where's my number color? Here we go. 33.996. So I'm going to go ahead and round that to 34. Awesome, but I'm not done. I have this 10 to this, okay? So when I have these 10 to this, let's take this over here, okay? So right now I have 10 to the negative 11th, 10 to the 24th. They're on the same line here, so we know we're going to add these two guys, okay? So we're going to add those exponents. Negative 11 plus 24. And the fact that now we have this on the bottom means that if it's on the bottom, I'm going to have to subtract it, okay? So I'm setting it up this way. So I'm going to end up with my 10 to the is going to be whatever negative 11 plus 24 minus 13 is. So if I do negative 11 plus 24 minus 13, what do I get? I get 0. Awesome. So what is anything raised to the 0? Anything raised to the 0 is 1. Okay? Oh, cats, come on. Cats and physics, you guys. So now all I know is that this is 34 times 1 newtons. So my answer is 34 newtons. Boom. And that's with this 3.5 kilogram mass, okay? So hopefully that one makes sense. Let's move on to the next one. Okay, you guys, let's look at this question again. The question was, what is the force of gravity on the rock from the earth? And we said that downward was negative. So actually part A of this should be negative 34 because we're saying the force going down is going to be negative. So FG, negative. Okay, so if you put in your answer what's a positive and you got it wrong, you probably just need to switch to the negative. Part B is what is the force of gravity on the earth from the rock? So now we're saying if this is the earth, the rock is pulling it up with some amount. So it's going to be the exact same number, but opposite. So for B, it should be the positive version of whatever your answer is for this, okay? What is the force of gravity from the earth on a rock that is twice as massive? So we know because of the way our formula works, it's just g m1 m2 d2 squared, or d squared, sorry. We already did all of this work for it. Oh my goodness. If I'm going to double that mass, it would be like I'm just adding a times 2 right there. So I'm just going to do times 2 down here. Okay, so I'm going to take this, I'm going to say, was the force of gravity from the earth on the rock. So that's going to be the one pulling it down. So it's going to be negative 34 times 2 newtons. So it's going to be negative 68 newtons in my case. Again, check your work. Make sure you're doing the right answer or the right numbers, okay? All right, next one. Okay, if you go back and you look, let's look at number 3. So number 3 is down is now positive, okay? So now we're going to say, whereas here it said down was negative, the rock being pulled down, it was negative. Here we're saying down is positive. We have an 87 kilogram person standing near the surface of the earth. What is the force of gravity on that person from the earth? Oh my goodness, it is exactly like this one. What is the force of gravity this was on the rock from the earth. Now it's on the person from the earth, okay? So we are going to do the exact same thing we did here, except in this case, instead of the mass 1 being 3.5, it's going to be whatever the mass of your person is, okay? So that means way back in all of this work, this beautiful work that you did already, you're going to set up the problem the same way. How can I get you to see this? Hello. Ooh, hello, hello. Here we go. Say the same way you did here. So 6.67, that's G, times 10 to the negative 11th. Here we go. Times, now this was mass 1. Well, mass 1's changed. Mass 1 is now whatever the mass of your person is. But the mass of the earth has not changed, so that's going to stay the same. And so is the diameter or the radius of the planet, so that's going to stay the same. So the only thing that's going to be different is now you're going to put a different number. Like for me, it's 87. And then you'll say 6.67 times 87 times 5.927 times 10 to the negative 11th times 10 to the negative 20, or blah, blah, blah. Everything we did before. Cancel things out the exact same way. You'll notice you still have to square this, okay? You still end up with these numbers on the bottom. You still end up with 10 to the 0. It's just that this number will change. So you have to make sure that's different. And also now we're saying that it's positive going down. So you have to make sure that number is positive. So in 3A, you should end up with a positive number. Okay, cool. Now let's look at part B of 3. So part B of 3 says, what is, boop, here we go. If a person climbs a mountain that is 450 meters high, how much less will the person weigh? How much less will this person weigh? It is insignificant. It is basically 0. Okay, you're not going to weigh anything less because right now our distance is 6. Where is it? Where did it was 6, 3, 7, 8, 1, 0, 0. Okay, now I'm going to add a new little bit of distance. Okay, so plus 4,500. Okay, so now my distance is going to be that giant number, which is super giant, 6, 3, 7, 8, 1, 0, 0, plus 4, 5, 0, 0. Okay, so now my distance is 6, 3, 8, 2, 6, 0, 0. But remember, we're going to end up squaring this. So if I square this, 6, 3, 8, 2, 6, 0, 0, then I end up with 4.07 times 10 to the 13th. That's exactly the same thing I had before. Okay, so you'll notice if you round, you don't change this. Okay, so it's such a small change, it doesn't matter. So you might round a little bit differently, and you end up with 4.07. No, it's if you don't. There's no way to round this differently. So it's going to change by 0. How much less will the person weigh? 0. You're going to weigh exactly the same. Okay, and don't forget your unit for this. If it's force, it's a Newton. If it's mass, it's going to be, it's still Newtons. All right, etc., etc. I think you should know how to do these now. A mass, so down is negative again, so you're going to end up with a negative number. What's the force of gravity on the person from the Earth? Again, we have a new mass, so change that out. Okay, but now in the second one, we have a person then goes to Mars, which has a mass of this number. So this is your new M2. Okay, so when you set up your problem here, okay, your mass, this was the mass of the Earth. Instead, now you're going to plug in the mass of Mars. Okay, and then for the distance, you're going to plug this in. And so remember, you have to square that distance. So let's actually do this one real quick. All right. So in this case, we have mass 1 is 87 kilograms. Yep, sorry, mine is, if I look at mine, mass 1 is 76 kilograms. I now know that, and I'm not solving A, make sure you solve A, okay? Mass of Mars is going to be my mass 2, and that is 6.419, and it says E plus 23, and there's a 1 here, it doesn't really matter. 70 times 10 to the 23rd kilograms. And the radius, or distance, is 3397000 meters. And I know that G is 6.67 times 10 to the negative 11th. So now I have everything I need to solve for force. Okay? So when I'm solving for force, remember F, G equals G, M1, M2, over distance squared. So I'm going to go ahead and set these things up. Remove my Indian food first. I'm going to go ahead and set these things up in their different colors so it makes it easy to move things around, okay? So G never changes, okay? That gravitational constant, which by the way is Newton meters squared per kilogram squared, is always going to be 6.67, I don't remember what colors I had before, times 10 to the negative 11th, and then Newton meters squared per kilogram squared. Okay, that's awesome. Now remember, your first mass is that person's mass, whatever your mass is for your person. So mine's 76, and that's this color, kilograms. Okay, and then times the mass of Mars times, which we have as I have 6.4191 times 10 to the 23rd, move it, cat, kilograms. Awesome. And then I have to put on the bottom my distance. So my distance is in numbers 3397000, and then no times 10 to that, but times meters. Oh, and don't forget that's squared. Okay, so now let's go ahead. I'm going to square this number just so I can start getting that thing in order. So let's see. So 3397000 times 3397000. Okay, so now I find out that on the bottom here, I have the number 1.15 times 10 to the 13th, because it says E13, and that is meters squared. Awesome. Cool, so what did I have on top? I'm going to rearrange. So I have 6.67 times 76 times 6.4191, and then I have times 10 to the negative 11th times 10 to the 23rd, and then unit-wise, I have Newton meters squared kilogram squared, because I'm going to do kilogram times kilogram. And let's make sure things cancel. My meters cancel. Where did my kilogram? Oh, I forgot to put this. I forgot to continue this down. Okay, so kilograms squared. Boom, boom. And I'm left just with newtons, so there is my unit. That's good. I can do my 10 to this. It's going to be times 10 to the negative 11th plus 23 minus 13. Okay, and then I'm just going to multiply these out and divide by 1.15. So it is, calculator, 6.67 times 76 times 6.4191 divided by 1.15 is a giant number. Okay, well, it's not super giant. Okay, so you end up with 2829.5 times 10 to the, it would be 23 minus 11 minus 13 times 10 to the negative 1. Okay, so 2829.5 times 10 to the negative 1 newtons. That could be your answer. But if it's times 10 to the negative 1, that means we're going to divide by 10. Okay, so we're actually going to move that decimal over once, so we can just get rid of that. And you end up with 282.95 newtons. So you should get something in the realm of that for your answer. Okay, and the interesting thing is if you did the one before this correctly, where you use the earth and everything, you can see what the difference between the two things is. Okay, that's what they're going for. So that was number 4. Okay, cool. What's happening in number 5? We have a mass. We have a seconds. Oh, how can we find how fast will the person be moving after falling for 1.5 seconds? Oh man, can I do anything with our good friend FMF? Okay, so if I know that F delta T equals M delta V, can I figure this out? How fast will this person be going? Oh no, how do I figure the force out? Oh my God, you're actually gonna have to solve using F1, this whole thing again. You're gonna have to use this. Except in this case, you're gonna have, so you know the mass of this is gonna be the mass of the Earth. You know, this is the distance from from the surface of the Earth to its center. And this is gonna be the mass of your person, and that is G again. So you solve for that F, okay? You plug it into this, you have the time, you have that mass, and then you're solving for VF, but you know that V, the initial, as soon as you start falling, is 0. So really you can change this to V, because this is VF minus V initial, and since that's 0, you can make it, you can simplify it to F delta T equals M delta V. This only works if your initial velocity is 0. Okay, so then in the second one, how fast will a person who's 184 kilograms be moving after falling for the same amount of time? Well, you could set this whole thing up again, or you could notice that 184 is just 92 times 2. Okay, so could we set this up so you know the force is now going to be twice as much? So then you could just say, I'm not going to do the whole problem again if I know I can just multiply whatever force I got here by 2, and then multiply by time, divide by the mass, and you get the delta, or the V final. Okay, I hope this really helped you guys. You're going to do great. Bye.